Okay, good afternoon, everyone. Today we're very happy to have Yohei Ema from University of Minnesota to tell us about on-shell construction of massive amplitudes.
Thank you. Thank you for the introduction and thank you for having me here. So it's actually I used the Chicago airport for many times because of the transit, but it's my first time to go outside of Chicago airport. So that was really nice. So today I'm going to talk about this massive scattering amplitude, on-shell construction of it. This talk is going to be based on these two papers. So we published one paper 2 months ago, and this is about QED, and we are also writing another paper about electric theory. So we started writing a draft, but I don't know when we'll publish it. So hopefully before October, at least. And this talk is going to be based, these papers and in collaboration with a bunch of, all of them are Minnesota people. So we have Tina, Wenchi, and Jan, Feynman. So we are kind of a big group. Okay, and this is the outline of my talk. So I don't know, how much you are used to this kind of on-shell scattering amplitude. So I just to be sure that we are on the same page. So I will just start from basics. So this section 1, the introduction part, is going to be really like a reviewing, show the review of the on-shell recursion relation. And then after that, I'm going to talk about there I will explain that the moment shift is a very important idea for those kind of on-shell construction. And then I will introduce our moment shift, which we call the all-line transverse shift or LT shift in short. So I will introduce that moment shift. But in order to explain that, I have to also briefly explain the massive spin formalisms. So I will also do some review about this massive spin helicity formalism. And after that, I will apply it to the QED. And then finally, I will apply it to the electric theory. So that's the outline of my talk. So this is about the paper we published 2 months ago. And this is the paper that we are now finishing. Okay, so the introduction. So today I'm going to talk about the on-shell method of computing the scattering amplitudes, especially two-level scattering amplitudes. And this on-shell method is an alternative way of computing the scattering amplitude. So we usually use the Feynman diagonals and so on so forth to compute the scattering amplitude. But in this formalism, you don't quite use the Feynman diagonals. You use some diagram that is similar to the Feynman diagonals maybe, but for visualization. But essentially, you don't use any Feynman diagonals, and then it relies only on the on-shell quantity. So that is sort of the key idea. And then in this method, as I will explain in the next slide, so the key point is that this kind of method recursively construct the higher point amplitude from the product of the lower point amplitude. So for instance, you compute a 4-point amplitude as a product of the 3-point amplitude, and 5-point amplitude as a product of 4-point times 3-point amplitude, and so on and so forth.
But are these like tree-level or loop or everything?
So I'm going to talk only about tree-level in my talk because of the reason I will explain in the next slide. Yeah.
But does it are there formalisms which extend it to loops?
So it's not a straightforward extension. So I will explain that. So in a tree level, the important point is that in a tree level, the amplitude only has the poles, right? Where the interlinear particles are going on shell. If you go to the loops, then you will have the cards and so on. So first, the analysis will be kind of different. And in that case, people use what is called generalized unitarity and so on and so forth. So that is sort of slightly different. Like a technique, maybe related, but slightly different technique. So today in this talk, I'm going to talk only about tree-level amplitudes. We are kind of wondering whether we can extend it to the loops, but that's more like a future. And we don't have any concrete answer yet. But that's something we are thinking. But today I'm going to focus only on the tree-level amplitudes. Yes. Right. So it recursively constructs higher point amplitude from the lower point on-shell amplitude. So that's sort of the idea. And it offers, I don't say always, but sometimes a more efficient way of evaluating the scattering amplitude. Like for instance, I think the most famous example is the so-called Park-Taylor formula, which is the gluon scattering amplitude, endpoint gluon tree-level scattering amplitude. And then this is kind of color order, so the color factor is already stripped out. And if you say that you have n gluons, but then 2 of them are having the negative helicity, and the others are having the positive helicity, then your amplitude is given by this. So this is the like a spinor quantities. I will introduce this data, but it is related to the momentum. So you can write down, you can express the amplitude in very simple way like this. But then in order to derive this from the Feynman rules, especially if you go to a very a high point amplitude like 6 or 7 or 8, then you have to really do a lot of computations. But by using this kind of on-shell method, you can actually show that this holds to all orders in terms of the number of the external index quite easily. So sometimes offers more computing the scattering amplitude. And I would say that this kind of technique is best developed for the massive theory. And then our focus in this talk, as the title suggests, is more on massive theory and what we can do with the massive theory. So that's going to be okay. And then in this slide, I want to review what is the basic idea of this on-shell recursion relation. Okay, so the key idea of this on-shell recursion relation is to deform the external momentum in this way. Okay, so you in general have like an endpoint amplitude that has like n external particles, and each of them have the momentum. So I say like the momentum of the particle 1 is p1, and then particle 2 is p2, and so on and so forth. So this I runs from 1 to n. And then the amplitude is in general a function of this external momentum pi, but you shift this momentum in this way. So the pi hat, which is given by pi plus z times qi. And then this z is a complex variable, and this qi is the how you shift the momentum. So this qi is your choice. So you choose some specific qi, and then you shift the momentum by using this complex variable z. So if you do this, then you can think of this external momentum as the function of this z, complex variable z. And then because the amplitude is the function of the external momentum, then after doing this momentum shift, you can also think of the amplitude as a function of this z. So you can think of this amplitude as a complex function of this one variable z. Okay. And in general, as I said, it has poles and cuts in the complex z prime from the intermediate particles. The cuts are usually coming from the loops and so on. But in the following today, I'm going to focus only on the two-level amplitudes because that simplifies my life a lot. In particular, if I say that I focus only on two-level amplitudes, I have only poles in this in this amplitude. So this amplitude has only poles where the intermediate particles are going on shell. So it's like what it is doing is that by changing this z, you're kind of changing the configuration of the external momentum, and in some cases, like you can, for instance, take the s, the center mass energy to be kind of zero by choosing the external momentum. So you are complexifying the momentum, and you can do such kind of things. And then there you have the pole. And then once you do this kind of momentum shift, then you can do the Cauchy theorem. You can do the complex analysis. So you start from this original amplitude, and then you can express the original amplitude in this way. Because here in this integration contour, we are just running the pole at the origin. So this pole is just coming from this choice of the integral. Like I put this one over z, so that's why there's a pole here. And if I pick up the pole here, then I just get a n hat, where z is equal to 0. That is just the same as the original amplitude, right? But then we can deform the contour, the integration contour from this. And then, as I said, it also has several poles in different complex planes, and then those are corresponding to some particles going on shell. And we can just deform the contour in this way. So originally we were having here, but then we now pick up the poles here, 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 and then we also have this convolution from the boundary. Okay. So we can express this expression in terms of the sum of the residue of those different poles. And also the boundary convolution, B infinity is coming from this convolution at the z is equal to infinity. And then at each pole, we can factorize the amplitude because at each pole is corresponding to some particle going on shell. So at that point, you can actually factorize the amplitude into the lower point, the product of the lower point amplitudes and the propagator. So this is sort of the factorization at on shell. And here the essential point is that if you can set up B infinity and this convolution is equal to 0, then you have only this convolution. And this convolution tells you that your original amplitude AN is given by the product of the lower point amplitudes. So, okay, so here in general, so this is going to, like if this is 4-point amplitude, this is going to be 3-point amplitude and 3-point amplitude. Okay, and then those are on shell. So you can express the higher point amplitude as a product of the lower point amplitudes, lower point on shell amplitude if B infinity is equal to 0. Okay, so that's sort of the basic idea of this on-shell recursion relation. Okay. So as I said, so this is the expression you get, and then so as I said, if we can ignore, so if we can say that this B infinity is equal to 0, then we have this expression. That means that we can construct the higher point amplitude out of the lower point amplitudes. And then people call that as the on-shell constructibility. So the on-shell constructibility is equivalent to say that B infinity is equal to 0, and that is equivalent to say that if we take the z to be infinity, its amplitude with some momentum shift drops first, because this B infinity is coming from the convolution of the boundary. Okay, The condition to have this B infinity is equal to 0. So there are two conditions that you have to satisfy to have this kind of situation. One is about the theory itself. So you have to, you should not have any independent conduct interaction to have this kind of situation. So here, the independent conduct interaction, I mean, is for instance, the scalar formal interaction of the phi to the fourth, or the higher dimensional operators like Euler-Heisenberg to the fourth or something. I think that this example is the easiest to understand because if you have lambda phi to the fourth, then your 4-point amplitude of the scalar fields is just like lambda, right? And even if you shift the momentum, this lambda doesn't change. So it doesn't drop as z goes to infinity. Then this lambda conservation will appear as this infinity. In other words, so the idea is you want to reconstruct a 4-point amplitude out of the 3-point amplitudes, but for this lambda phi to the fourth, a 3-point amplitude doesn't know anything about these 4-point amplitudes, right? So that's why it appears as a boundary term. So this is sort of independent conduct interaction, and that should be coming from B infinity. On the other hand, the gauge 4-point interaction is different because in a Feynman diagrammatic language, we have this gauge 4-point interaction like a gluon 4-point interaction or something, or also WW and so on and so forth. But those interactions are intrinsically related to the 3-point interaction because of the gauge invariance or because of the gauge symmetry. So those are, even though you have those kind of contact interactions, those are dependent in the sense that the 3-point amplitude actually knows somehow the information of this 4-point interaction because of the gauge symmetry. So B infinity is equal to 0 requires the absence of the independent conduct interactions. But even if you have those kind of dependent conduct interactions, you can actually have the situation where the B infinity is equal to 0.
Does quantical superstring theory independent or dependent?
That's right. So if you impose a supersymmetry, then this lambda can also be related to other stuff. And in that case, then yeah, you can. So here I'm just assuming the simplest case, where you just have the phi to the fourth. Yes. Yes. Yeah. Right. Okay. Yeah, I actually put some nodes without a Suzy and then I erased it, but I should have kept it. Right? So yeah, that's right. And then the second condition is that even if you don't have any independent contact interaction, still you have to be kind of clever, smart, in the sense that you have to choose a good moment shift. So it still also depends on how you shift your momentum. So the choice of this Qi. So remember, so we shifted the Pi to Pi plus Z times Qi. So this choice of this Qi, is going to be important to have this vanishing boundary term. Okay. And a good moment shift is widely known in the massive theory. So I think the most famous one is the so-called BCFW shift. But then our contribution in our paper is that we found a good shift, that works for the massive theory, and that is we call it LT shift. I will explain this more details later, but the key point is that we shift the momentum by the transverse polarization vector of the same particle. So yeah, this is shifted by the transverse polarization vector, so that's why we call it transverse. We shift all of them, so that's why we call it all-line. So LT stands for the all-line transverse shift. Yeah.
So where is the assumption about the high derivative terms coming into the story?
Sorry?
So you're assuming the absence of things like f nu to the fourth and any other.
Yeah.
Okay.
I think you will see that later because later I will discuss the Nazi behavior of the amplitude by using dimensional analysis. That you can actually input that information as a mass dimension of the couplings. So yeah, I will explain that later, and maybe you can ask later.
Is it sufficient to require that the theory is renormalizable?
So yeah, that's one condition you can impose. Yeah, for instance, yes.
Lambda phi fourth.
Yeah, then how-
Yeah, except.
Yeah, except lambda phi to the fourth. Yeah, so what I will discuss in the following is that by using this LT shift, you can do the recursion relation for like a 4-point amplitude, 5-point amplitude, 6-point amplitude, and so on and so forth, like all the higher point amplitude, except for this lambda phi to the fourth.
So a theory with a fixed potential with a 5-4 interaction is bad, or is not going to be addressed?
That's not bad because you can still compute it. Like it just appears as a B infinity.
Okay, so you have to compute the B infinity.
Yeah. So in that case, you cannot say that binary term is equal to 0 based on some general argument or something. So you have some finite term there, and that is your input. So in the Lagrangian case, you have to just put this lambda phi to the fourth just by hand to the Lagrangian. In this case, you have to put this information of lambda as a boundary term just by hand
into B infinity.
So yeah, at some point you have to input that information.
Presumably, if you want to do BCF, all these machineries, it should be
not for the lambda 5/4. So lambda
It's not for
5/4,
the lambda 5/4.
we know the amplitude. It's lambda.
Yeah.
So presumably
yeah,
for
yeah.
some harder cases.
I think, yeah, the amplitude is just lambda, so there's no Warner shift, right, that works in that case, except for Suzy. Like in Suzy case, I think you can also do the super Warner shift or something, but yeah, except for that. Usually. Yeah, so this is sort of the end of the introduction, so if you have any further questions, like you can ask. Yeah, looks good.
Just to hold on. So how much of this story do you think will go, or maybe I'll ask you at the end. I'll ask you at the end.
Okay. Yeah, sure. Maybe I can just go ahead and you can ask later. Yeah, so this is the end of the, a very short review of this Armstrong recursion relation. And then from now, I want to introduce our LT shifter in more detail. But before that, I have to explain some massive spinor helicity formalism. So I try not to use this as much as possible, assuming that you guys are not that familiar with this massive spinor formalism. Also partly because I'm also not that familiar with it, because I started this project since the last year. But anyways, I have to explain it a bit, so I will do that. Okay, so usually we express the momentum in a vector space. Like we usually think of the momentum as just p mu, right? So mu is the vector index. So we usually express it as it's just a vector in the 4-dimension. But remember, so when we learn this representation of the Lorentz group, we learned that vector representation is equivalent to 1/2 of this. I forgot what it's called, A spin or B spin or something of this SU2, SU2 times SU2. So equally, so you can express the momentum by using this A and A dot indices. Like this is like these are just spins, right? Like A spin and B spin. And then so in practice, what I can do is you can contract this P mu with the 4-dimensional Pauli matrix and single mu, and you can express it in terms of sort of the matrix. Okay, so if you do that, then your momentum is going to be something like this. And from this expression, it is clear that the P scale is equal to the determinant of this matrix. And if you consider masses theory, then determinant is going to be equal to 0 because P scale is equal to 0. So in that case, you can express the matrix as a product of the two vectors, like this. One pair of the spinors. In the massive case, the situation is slightly different because P scalar is not equal to 0. So it is M scalar which is not equal to 0. So in that case, you cannot express the matrix in terms of just one pair of the spinors. So you have to actually use the two pairs of the spinors. This I will run from 1 to 2. And then this I is corresponding to the literal group index, because the literal group transformation is by definition some transformation that doesn't modify the momentum, right? And here, what you can do is that you can rotate this angle bracket and bracket and scale bracket, those kind of spinors by the SU2 transformation. And because the indices are contracted, so you can just make this quantity the momentum invariant. So that is the SU2 transformation. And SU2 is sort of equivalent to the SO3 transformation. That is, of course, corresponding to the literal group transformation of the massive particle. In this case, you don't have the SU2, but instead you can just rotate the face of this this quantity, and that is corresponding to the U1, and the U1 is equivalent to the SO2, and the SO2 is the literal group transformation of the massive particle. So those indices are corresponding to the literal group indices. Okay. And then we can further fix. So this tells you that determinant of this matrix. So you can also think of this as a matrix because it now has this 1, 2 like an index. And then the determinant of this is equal to M scalar, means that the determinant of this matrix and this matrix, the product of them should be M scalar. And we can just fix the normalization to be like this. Once we do that, then we can show that this angle and square bracket satisfy those kind of relations, and this is nothing but a Dirac equation. So that tells you that you can express the Dirac spinors like a U and V spinors in terms of this square and angle brackets. Okay, so the key point is that those are just nothing but those U spinors and V spinors. And then we sometimes use the so-called board notation, maybe not that much, but we sometimes use the so-called board notation, where we, instead of writing down this I and A, we just say this is like a board I. So board I means that it actually has this floating literal group index. Okay. And then contraction, raising and lowering the indices are done by this epsilon tensors. And so this is for like this A and A dot, but you also do the same for, obviously you do the same for the digital transformation because that is also SU2. Okay, so this is the massive spinor formalism. And then, in particular, in our model, so in order to define our model shape, we choose a particular basis for this decomposition. So we choose what is called the helicity basis, where PI is given by this, and then I and AI are given by this kind of expression. So I think, so this is sort of the helicity basis. And in particular, if you take the relativistic limit, sorry, the mass goes to 0, then this AI is going to be proportional to M. So, these are subdominant and these are dominant components. So we just use this decomposition. Once we use these kind of explicit forms, then we can just express the polarization vectors also in terms of these, spinor helicity quantities. So the plus polarization or minus polarization, they are given by this, and longitudinal polarization is given by this. Okay. Especially the transverse polarization vector has a smooth massless limit because the Li, as I said, is proportional to M when you take M to be 0. So that is cancelled with this 1 over M. So it has a smooth relativistic limit or massless limit. In that case, like if you take the massless limit, then this AI, the choice of AI is going to be somewhat arbitrary because it doesn't appear from this expression. So massless case, we can take the AI and this AI to be arbitrary. So that is the so-called reference vector. So there is some ambiguity about defining the polarization vector. And then if you choose a different reference vectors, and that is corresponding to shifting the epsilon mu to epsilon mu plus p mu in the vector language. And that transformation is just corresponding to the gauge transformation. So even though you have this kind of ambiguity, that doesn't show up in the harmonics, in a physical form. But anyways, you have such kind of. And then, so the important point, so the details are not important. The important point is that once you use this spinor helicity language, you can express the Dirac spinors, the Dirac wave functions, and also the polarization vectors in terms of the spinor helicity quantities. Okay, and then we define all line transverse shift in this way. Okay, so I'm concerned in the case where you have either fermions or gauge bosons, and then the fermions and gauge bosons both can have the helicity plus, and if the helicity of that particle is plus, then you shift I to the I plus Z times Ci times Li. We shift the angle bracket. I will explain that. I will explain soon why I chose this relation. And if it is minus, then I will shift instead of a square bracket in this way. And if it is longitudinal, I shift the angle bracket in this way and square bracket in this way. There's actually an alternative choice, but that choice doesn't matter, so I show only one choice here. Okay. And the reason why, so first of all, as I said, in a vector notation, this shift is expressed as a pi hat is equal to pi plus z times ci times mi times epsilon I. So we are just shifting the momentum by the transverse polarization vector of that particle. And then this is first of all nice because it satisfies on-shell condition unchanged, like a pi hat scalar is equal to pi scalar, which is equal to mu scalar. That you can see from this expression, for instance. And in particular, the reason why we chose this kind of moment shift is that if we do this, then the external wave function and also these polarization vectors are not shifted. For instance, you can look at this epsilon plus. Epsilon plus doesn't contain this angular bracket of this I. So even if you shift this angular bracket of this I, this epsilon plus will not be shifted. And then the same is true for this epsilon minus and epsilon L and so on and so forth. The reason why I want to have this is that, as I say, in order for the on-shell constructibility, I want to have a better behavior to that Z, right? So if I get some Z factors from the external wave functions or polarization vectors, that in general makes the last behavior worse. So I don't want to have such kind of behavior. So that's why I chose this specific choice of the moment shift. Okay. So that's really the idea behind this choice of the moment shift. And then total moment conservation. So first of all, this moment shift should also satisfy the total moment conservation because the amplitude should satisfy the total moment conservation, which is just a summation of this Qi should be equal to 0, and that is equivalent to this kind of expression. And this equation has a non-trivial solution even for the proper amplitude because so it has 4 equations for the 4 variables, and the overall scaling is not important. So naively, you might think that there is no non-trivial solution. The only solution is a Ci is equal to 0, which is nothing but you're not shifting any amplitude, but that is not true because the temporal component of the transverse polarization vector is equal to 0. So it actually has a solution, non-trivial solution for this CI, even for the four-point amplitudes. So that's another good point. Maybe this is a bit of a technical detail, but that is another good point of this shift. So we do this modal shift. Okay. So this is our shift. So this is sort of the introduction of the LNT shift. And after that, so first I want to apply this to the QED. So I want to go into the actual computation. So far I discussed more or less the basic formalism, but from now I want to discuss how we can actually apply it to some real amplitude computation. So yeah, so this is the end of this part. So if you have any further questions, then ask me. Okay, then I can just move on. So first, so I want to apply this to the QED amplitude, but first I want to argue that this LT shift, if you apply it to the QED amplitude, then you can just say that B infinity is actually equal to 0. So I want to study the Larcy behavior of this moment shift under of this amplitude under the moment shift under the LT shift. Okay. So first of all, schematically, you can write down AN, the amplitude in this way, as a summation of some different diagonals. So here I'm a bit cheating because I say I'm not using the Feynman diagrams, but here I'm sort of using the knowledge of the Feynman diagram, but not that much, I'd say. Okay, and then this diagram, you have convolution from different diagrams, and then this G schematically denotes the collection of the couplings you have. Okay, and then this F is the kinematic function, so it contains some kinematic factors. And on top of that, you have to trace this kind of factor with the external polarization vector and external wave function u. Okay. So this is sort of the general form of the amplitude you get. And then, so first of all, the endpoint amplitude has the mass dimension 4 minus n. So that means that if you count the mass dimension of the left-hand side, that should be equal to the mass dimension of the right-hand side, of course. So that means that 4 minus n is equal to the mass dimension of this collection of the couplings and this kinematic factor f, and nf divided by 2, because each wave function of the Feynman has a mass dimension 1 over 2. So you can write down this kind of general equation. And then in our momentum shifts like ALT shift, as I said, like epsilon and u, so these external wave function and the polarization vectors are not shifted. So that means that entire z dependence of this amplitude is really coming from this f factor. Okay, and then in this f factor, so if we want to discuss the Larcy behavior, so first of all, the denominator, which is coming from the propagator of this f, will always contain this scale term in general. And then numerator, you can pick up at most one z for each mass dimension, because z is always coming with qi, which has a mass dimension. So you pick up at most one z for each mass dimension. So that means that if you say that a hat n is going to behave like this, like z gamma, then gamma should be smaller or equal to the mass dimension of this f, which is just equal to the 4 minus n minus g minus nf divided by 2, because you can use this equation. And then here, so here it is an answer to the previous question. Like here, I actually have this mass dimension of this g. So if I say like if I have some higher dimensional operators, I say like this g is going to be like a -2 or -4 or whatever. If I say that I consider only the renormalizable theory, then I can say that the mass dimension of this g is going to be greater or equal to 0. Okay, so it's positive or just equal to 0. And if I require, so in the rest, I'm going to just talk about the renormalizable theory. So in that case, I can just say this kind of thing. In that case, I can just say that gamma should be smaller or equal to 4 minus n minus nf divided. Okay. So from this expression, and then the onshore constructibility is equivalent to saying that gamma is negative, because in that case, B infinity is equal to 0, because the hat n drops at the Larcy. Okay. So from this expression, you can say that if you consider like n larger than or just equal to 5, then this is negative, independent of whether we have the fermions or not. So that amplitude is onshore constructible. And if n is equal to 4, but with the external fermions, like you have some finite number for this, like for instance 2, then again this gamma is going to be negative. So that means that we can onshore construct that scheduling amplitude. So that is our general argument based on the dimensional analysis. This doesn't tell you that, for instance, so later I will consider W scattering, and this equation alone doesn't tell you that W scattering is reconstructible, because W scattering case, for W scattering case, this n is equal to 4 and this nf is equal to 0, so you just get gamma should be smaller than or equal to 0, and 0 is allowed. So this dimensional analysis by alone doesn't tell you that W scattering is reconstructible, but there, as I will explain later, I can use the Ward identity to further argue that the actual behavior is better than this. But for the QED, this equation, this discussion is just enough. So here I just presented it, but I will explain Ward identity in the last part of my talk.
How about photon? Photons, if one of the particles is a photon, does it?
You can also use the same argument for the photon.
The same as WW?
Yeah. Yes. Okay. But in this section, I'm going to talk only about this E plus E minus going to E plus minus process in the QED with our LT shape. And then, so one reason is because this is the simplest example, and if we try something new, then we should start always from the simplest example. So that's part of the reason why we wanted to compute this amplitude. If you assign a flavor in this way, you even don't have any T channel, U channel process. But at the same time, the other reason why we started thinking about this process is because there were confusions in this process in recent literatures regarding the conduct term. So I don't explain any details about this paper, but the key claim is that this paper tried to reproduce this E plus E minus going to mu plus mu minus process by using the on-shell method, but they failed to get the correct amplitude, or they had some ambiguities, depending on what kind of equation you use, you get a different result. I don't explain the details because I think the main reason why they got this kind of confusion is just because they didn't discuss the moment of shift to reconstruct the amplitude. They sort of just glued, they just took the product of the 3-point amplitude, but without doing the moment of shift. So their 3-point amplitudes are not an on-shell amplitude in a sense, or their photon is not on-shell, their intermittent photon is not on-shell, so that's really the reason why they got this ambiguity about the conduct term. But I don't explain the details. My message is that if you do the proper thing, in a sense that if you do the moment shift, then you always always get the correct result. So that's my message. But the reason really why we started from this example is that we want to make sure that if we do the moment shift properly, and then if we do the computation, then we get the correct answer. So that's what we wanted to check. Okay. And then now, as I said, in this process, we have this gamma, which is equal to -2. So that means that B infinity is equal to 0. So this is on-shell constructible. So we can just forget about B infinity, saying that this J is or 0. And then in this case, we have only the poles that the P12 is equal, P12 scalar is equal to 0. So I use a shorthand notation like P12 is equal to P1 plus P2. If I write down Ij, that means that Pi plus Pj. And then this equation actually has two solutions because this contains up to the z-scalar term. So I denote that solution as z plus minus the complex conjugate of each other. And then this point is the point where the intermittent photon becomes on-shell. So the S-channel pole, you are hitting the S-channel pole. So F4 is sort of schematically given by this kind of expression. And then in practice, what you get is that you get a summation of the residue of this expression, where Pi 12 is going to be equal to 0. And then, as I said, you can use a factorization, so you can express this in terms of the product of the cubic interactions. And here you can use this kind of expression, it has 2 poles, and you can just extract this P12 scalar factor. So by using this kind of expression, and by picking up both Z12 plus and Z12 minus, you get this expression. Okay. And here the lambda is corresponding to the helicity of the intermittent photon. Okay. So the important point is that here now you have this product of the 3-point amplitude. So the 4-point amplitude, original 4-point amplitude is expressed in terms of the product of the 3-point amplitudes. Okay. So what we have to do now is that we have to evaluate this product of the 3-point amplitude to get this F4. And so because of the lack of the time, so I will not explain any details, but in general, the 3-point amplitude regardless of whether we are talking about mass theory or mass theory, so three-point amplitude can be constructed in general from the little group covariance, and it is discussed in this paper by Feynman and von. And then, so I don't explain in details, but the bottom line is that they can write down this kind of interaction. Like by using this little group covariance, you can write down this kind of interaction as a minimal interaction between the fermions and the photon. Okay. So they use what is called the X factor, X12, which is given by this. And I think I have already explained this 1 and 2, and also this I. But there's also this psi spinors, and those are kind of corresponding to the reference spinors of the photon. So as I said, like photon polarization has ambiguity, that is corresponding to the gauge transformation, and that is corresponding to disk size. So disk size is called the reference vector, and that is corresponding to the gauge degree of freedom. But and then as I said, and then disk size ambiguity doesn't show up in the final result. And then if so in our computation, this I, the intermediate photon particle, is always on shell. So that means that for on shell particle, we can so we have to think only about on shell photon. And if we consider only the on shell photon, then we can in general show that this product is given by this. So we have to use some identity of the spinors and so on. So first, I will not show the technical details, but the bottom line is that we can actually show this equality between this expression and this expression. Okay, so this is true only for the on-shell photon. So if you are away from the on-shell configuration, then this equality is not necessarily, true. So that's actually the reason why, like in previous people got some confusion because they are not using the on-shell, like they are not really, using the on-shell photon. So they try to show this kind of equality, but sometimes they fail. So that was the confusion. But here, once you do the on-shell, the important point is that you have to use only the on-shell quantity. So there's no such ambiguity. And then, so as I said, the LT shift doesn't shift the external wave functions. So this 1 and 3, this ball notation, remember, so those are corresponding to the spinors with the floating little group index or indices. And those indices are corresponding to coming from the external wave function. So those are really coming from the external wave functions. We choose LT shift such that we do not shift the external wave functions. Then that means that in this final expression, we can just drop this hat, because we are not shifting those spinors, those specific spinors. So that's our choice of the moment shift. So this expression is independent of Z. And then we can plug this expression back to this expression, the original expression. So now we evaluated this product in our previous slide, and I said that this Z, it actually doesn't depend on this Z. So we can just put it outside of this bracket. Then what you have is that you have this structure, and this structure like a Z minus Z plus, because you have this conjugation from the other, like a complex conjugate of the pole. So this numerator actually cancels with this denominator. So what you get is that you in the end get this kind of expression. This correctly reproduces the Feynman dialectic result. So no conduct term ambiguity arises as opposed to, as I said, gluing without a moment shift that was done in this paper, for instance. And then we also do not need an explicit form of this Z12 plus minus, no CI used in the LD shift. So in this computation, so if I really have to solve the moment, like a total moment conservation equations and so on and so forth, then the expression for this CI is going to be complicated. But the point is that I actually don't have to do that because it just automatically drops from the final expression. And I think so it is certainly true for this specific example, and I think it is in general true. Like you don't have to really solve this CI. So that's nice. And then here I just explained this EE to mu, but in our paper, we also just to make sure we also repeat the same computation for the like a EE mu gamma amplitudes. And in principle, you can also consider like a EE mu tau tau, like a higher point amplitude by using this method. So yeah, that's what we did in our paper, which we published 2 months ago. So this is the end of the Q&A part, and then so if there is any question, like, you can ask me about this Q&A part.
In the Ema's original paper, do they do momentum shift? Do they do? I don't remember.
So
they discussed ECF.
You're talking about this paper,
Yeah.
right? Yeah. So in this paper, they didn't discuss a momentum shift. So their argument is that, so if you glue the amplitude, so they actually glue the amplitude without talking about a moment shift. The argument is that that correctly reproduces the pole convolution, the residue of the pole. That is certainly true, but there's an ambiguity of the conduct term that doesn't correlate with the pole. And then I think, the confusion of this paper is really about this conduct term. So, you can just reproduce the residue of the pole, but in general, that is not the end of the story. You, in general, have this conduct term kind of innovation, and then, there's an ambiguity. So that's, yeah.
And the shift that you described, like for the QED, like that's like a theory dependent shift that you are doing, like for different theories, you will do a different kind of shift.
It's not about a different theories, it's more about a different helicity of the external particles.
Okay,
So
so
what we are doing is that for plus particle, we do this shift. For minus particle, we do this shift. So if you consider like a different amplitude, like external helicity of the particles are different, then we do different moment shift for different like amplitude.
but in the very beginning, you said something about good momentum shifts or something like that. So, I mean, it seems to be just fixed, so, I mean, it's.
So this is not a unique choice. Like you can also do other like moment shift for like a different. I think our benefit is that we know that this works for all different combinations of the helicities.
Oh, I see.
But for some specific helicity combinations,
okay.
you can also do some other.
So that the Z behavior is nice. The large Z behavior is nice.
Yeah. So you have to argue that it is nice, but in some helicity configurations, then you can actually do. So for instance, the original BCF there with momentum shift, they actually also choose the helicity of the external particles. You usually shift the minus negative helicity particle and the positive helicity particle. So you actually choose the the particles you shift. So I think what is nice about this is that so in some cases, in some combination of the helicities, you can also do that moment shift. But what at least I personally like about this moment shift is that like it works for general combination. Like you have to do a different moment shift for different combination of helicities, but it is kind of working for every single combination. So that's, I think, yeah, that's the thing. Okay, then I guess I can move on to this electroweak theory for the last like 15 minutes or so. I think this part is, at least for me, this part is the most interesting. So happy that I can tell you. So from now, I want to compare the WW scattering, like a WW going to WW scattering within electroweak theory. Okay. And then, as I said, a 4-point gauge boson naively leads to this gamma, which is given by this expression. But if I consider like a 4W scattering, this N is equal to 4, this NF is equal to 0, so you get 0. So you cannot exclude the possibility of having gamma is equal to 0. So you cannot, just by dimensional analysis, you cannot argue that you can forget about the B infinity. But the actual behavior of this amplitude is better thanks to the word identity. Okay. So here, remember that the LT shift, the all-line transverse shift, is shifting the momentum by the transverse polarization vectors. So if you have at least one transverse mode as an external particle, like if you have one like a transverse W boson, then for that particle, for that transverse mode, this PI is going to be proportional to the external polarization vector if you take Z to be infinity. So you can, so it is just dominated by this term, not this term, right? So in other words, your external polarization vector is also proportional to the momentum. I'm just saying the equivalent thing. And remember, so in order to derive this equation, we have to we are kind of saturating the mass dimension by picking up like a Z-dependent part for each mass dimension. So that means that if we saturate this inequality, then what we have is that we have this A hat, which is like a Z 4 minus N. And here I'm assuming that particle 1 is transverse, okay? So then this epsilon 1 plus minus, and then you have some kinetic factor. But here I'm exhausting all the kinetic factor by using Qi. Okay? So the this is shifted momentum. Then because epsilon I plus minus is proportional to Qi mu, so that means that I get this kind of expression. And then here I can input the word identity as like information that, so I say that, I start from some like unbroken theory from the beginning, like spontaneously broken gauge symmetry or something. Then if you forget out, so in this case, we don't have any other massive parameters. So in this case, you can just say that, this Bode identity of the unbroken theory tells you that this product should vanish. So if you input, so this is more like an input in this formalism. So you can just input the Bode identity at sort of the galaxy, so that this quantity just vanishes. And if you require that, then you can say that this gamma is actually like this leading on town vanishes. So you can actually put this minus one here. So this is more like kind of on-shell way of saying that I'm starting from a spontaneously broken gauge theory. So sort of not exactly high energy, but at some dash c. So you actually have this kind of symmetries. Okay. So here, as I said, like I need one transverse mode. So it doesn't work for the 4 longitudinal like W boson scattering, but that is not a problem because in general the amplitudes are little bit covariant. So once you for instance reconstruct like one transverse amplitude, you can just flip. You can just add some spin raising or rolling operator to convert it to all longitudinal scattering. So it is just nothing but like when you compute, like also in the Feynman dynamics case, when you compute the scattering amplitude, you don't compute it for like
But sorry, I thought that at the very high energies for longitudinal scattering is the same as lambda 5/4.
I understand it. Yes.
And you don't have it here.
So I think we are kind of actually
You
wondering.
have to somehow add that by hand.
Yes, exactly. So I think here. So I don't have a complete understanding, or we don't have a complete answer. Our feeling is that this 4L, like in the 4L case, that we can actually show that this doesn't work, this LG shift doesn't work, it doesn't reproduce the correct amplitude. I kind of feel like that is related to the equivalence theorem. So here, what we are saying is that we input additional information that these longitudinal modes are actually related to the transverse W bosons. Otherwise, we can't.
I'm just saying you don't have enough information here to reconstruct that, right? So you, or do you? And I don't know the four longitudinal scattering.
So for longitudinal case, like just by the moment shift, you're not enough. Then you cannot reconstruct actually.
Yeah.
And then here, what I'm saying is that.
So even though you this presumably, I mean, it's not your argument here. You need a one transverse here, but.
I need a one transverse here. And then what I'm saying in this last line is that once you compute the amplitude with one transverse pole, then you can just flip like so the difference between transverse and longitudinal in the Feynman dynamic computation is that you just have this external polarization.
But on the other hand, I know for a fact that for longitudinal is not reconstructible because you need to add the 5/4.
Yeah.
So it's not just taking the transverse. It's not just taking the longitude. It's not just taking the transverse, doing this little transformation. You can completely capture that.
I think you can actually completely capture because in the Feynman dynamic computation, what you do in practice, you just compute the amplitude and attaching the external polarization vectors, right? And then you just have the choice, like either put this transverse polarization vector or longitudinal polarization vector. And depending on that choice, you actually get the longitudinal like a scattering. And if you go to high energy, then of course that is related to the like this lambda and so on and so forth. But in principle, what you do is that you just change the external polarization vector, right? So here my claim is that you can do that. But I think
you're saying that then you okay, even though it starts directly from longitudinal, it's not doable. But you can try to do this.
Yeah. Try to like just for instance, go back to this polarization vector representation and just change it. So you need an additional input. So I completely agree with you that 4L is different from like a one transverse. And then I think we don't completely understand why it is different, but our feeling is also more like because of the equivalence theorem and the lambda 5 to the 4th, you kind of reconstruct. So kind of feel like that is related. Yes. So that's actually I think really that's the reason why like we need this one transverse. Yeah. Okay. So as I said, so I compute this WW scattering, WW going to WW, and now due to mode identity, WW to WW scattering with one transverse mode has this relation like a -1. So that means that we can just say that B infinity is equal to 0, so it is on-shell constructible. And then so let's just compute and see if that really works or not. Okay. And this argument is actually independent of the presence or the absence of the Higgs, so we can just compute first without the Higgs. And see what happens.
So with Higgs or without Higgs is just the fact that whether you can factorize on the Higgs pole or not.
Yes,
So
yes,
you-
so, yeah.
You still have to somehow know something about whether this has a Higgs or not.
Yeah. So I think in the on-shell program, what you do in practice that you first specify all the particle contents you have.
Yeah.
And then you factorize and you just write down the general.
But this is a slightly, anyway, it's from 3-point amplitude.
Yes. So here what I'm doing is that first I just forget about the Higgs, like I just assume that there's no like Higgs in the spectrum and see what happens. And then so I compare, so we have like still have Z and gamma, so we have this kind of on the S channel and T channel. So in there like you have the summation of the different poles. So this summation is corresponding to this one on the internet particles on S channel and T channel. But again, like we get this expression that is the same as the previous like QD expression. And now again, we say that B infinity is equal to 0. So this lambda one should be plus minus. And then again, what we have to do is that we have to compute this product of 3-point amplitude to get a 4-point amplitude. Okay, and then so again, a 3-point amplitude can be determined by the true group covariance. So it can be written in this spinor helicity formalism, but I will use this vector like notation. Maybe it is a bit too messy, but the important point is that so first of all you have this WWZ coupling, and then from in this approach this is just some arbitrary number like this is a bottom-up approach. So you start from 3-point amplitude, so this coefficient is in general just like an arbitrary number, and you have the same for this WW gamma, and here the B is given by this kind of expression. It's messy, but the important point is that the Bartek function actually satisfies this kind of relation. So this means that when we compare the product of this S3, then we have the polarization vector sum, because we have the summation of the polarization of the internal vector bosons, and then this internal polarization vector sum can be replaced in this way, like because of this relation. So this epsilon mu can be replaced by minus eta mu, because the difference between these two cancels because of this relation. So you have this expression, and then you have to evaluate this product, and then what you have is the product of the Bartek functions like this, and then you can expand this expression. So each Bartek function is linear in this momentum. So if you write down the product, then you can in general expand this up to the z-scale term, like this V0, which is independent of this z, and linear term and a quadratic term. Okay. So actually, like a V0, V1, V2, they should have the Lorentz indices, but I'm just ignoring it. And from this expression, you can see that the linear term in this Z plus minus cancels between this convolution and this convolution, because you're gonna get like Z plus times Z minus and Z minus times Z plus, so they cancel. So you can just forget about this V1 convolution. And then this quadratic term, so you have this Z scalar term, you also, on top of that, you also have this Z plus term, you have this kind of structure, but by combining all of them, the quadratic term is given by this expression. And you can simplify it by using the solution, this is plus minus, then you can just show that it is equivalent to this expression. So what is nice about this expression is that you actually have this Pij squared minus Mi squared in the numerator, and this cancels with pole of the propagator, okay? So because of this relation, so you have the convolution from this V0, and that is corresponding to this first line expression. On top of that, you also have this convolution coming from this V2, and that is given by this expression. The important point is that in this expression, there is no propagator poles anymore, because that is cancelled with this expression. And this Z boson convolution and W boson convolution, they contribute equally to this second line. So this is sort of the constant term, and then that is arising from the Z-scalar term.
So the second line is like a contact term.
Yes.
Right?
Yes.
Is that unique? Because like you can have different choices of Z's. Like for massless theories, at least the contact terms are fixed by gauge invariance in some sense. But here, like, I mean, I might have a different kind of choice of Z shifts, and I can land up with a different contact term. Is that a possibility? Like,
what do you mean by the different moment? So here I'm just using one moment of shift, and then this is unique, right? So this is the answer you get.
suppose I use a different momentum shift.
I think if you, so, I mean, it depends on how you define it, but so the correct amplitude has a unique answer, right? Correct amplitude just have a, single quantum term. So if your moment shift is doing the good job, in the sense that you don't have any B infinity, then that should give you the unique answer.
But I'm saying that here you're saying that the correct contact term, because you know the theory, which is underlying it. But suppose I don't know the theory, someone just gives me that, oh, these are the particle spectrum, and like, I'm just trying to reconstruct the theory using this kind of thing. So I can do a different Z shift, which obeys all these kind of nice behavior properties. Is it possible that I can end up with a different contact term?
So I think if you define a theory in the same way, then you should always get the same quantum term, independent of how you shift the momentum, because you are starting from the same amplitude, right? So yeah, that's my, so also here, like, so just as a check, we are comparing this quantum term with the Feynman derivative result. So that is actually the topic of the next slide. Like, if we say that this, lambda one is transverse, then we can use this relation to simplify
Gauge
this.
invariance play the role.
Yeah. Here the gauge invariance really plays the role. Yes.
Okay, so there is gauge invariance.
Yeah.
Yeah.
Okay.
It is because of
So
okay.
I think it's different.
what
If
you
you
are-
say I wanted to have two charged massive gauge boson,
Yeah.
one neutral
Yeah.
gauge boson without anything else, then it's not unique.
Okay.
You have
Yeah.
to like somehow you have to.
So yeah.
Yeah,
So
yeah,
here
so, okay.
I actually
Yeah.
input the gauge invariance as an input because I assume that
Right,
is
right,
equal
right,
to
right,
zero,
right.
and that is given
Yeah.
by wall.
You already use the gauge invariance.
So I actually input the gauge
Okay.
invariance.
Okay, yeah,
So in
that
first
was,
one, you can also write down like
You know you can say it in a nicer way.
What?
If you are Nima, you will say you will discover the gauge invariance.
Yeah, I can also say that.
The
Yeah, right.
requirement.
Yeah. That's right. Yeah.
So is it a requirement here? Do you have to have a Higgs?
It depends on what you mean by your first principle. You can elevate something to a first principle, and require it, and then isn't that amazing that discover the gauge invariance?
You just need 2-to-2 scattering of massive vectors. from
Yeah.
perspective.
But no, but I think there are, depends on what you want to keep being fixed. You want to, for example, Weinberg has shown that you can actually discover gauge invariance by just wanted to estimate some amplitude that has good behaviors.
Yeah.
But that's the amplitude you can't see here, right? With the just the longitudinal polarizations. Isn't that usually the bad one that you have to unitorize with the?
I think maybe that is the topic of this
next slide.
gray pattern or something like that, so I can explain that. So yeah, maybe I can also list some properties of this computation. So first, so this reproduces the correct amplitude including quantum time. It should, and then it does. And then it does not need any explicit forms of the CI used in the LT shift again. I don't use that information. And also then I think what is nice about this computation, at least for me, is that the gauge component quantum term in the language of the Feynman diagram, it's derived from this discard part of the 3-point amplitude. So this discard part is really important to get this expression. So here in this computation, no Higgs is included. So the good Larson behavior is somewhat different from good high energy behavior in a sense. Like sometimes people say that Larson behavior is kind of equivalent to the high energy behavior, but for this specific choice of the model shape, that is not necessarily.
so by high energy, is it largest large T or largest at fixed T?
Like both S and T large.
Okay.
I think I can also take a different name, like
Mhm.
like a fixed angle or fixed T, right? Maybe I will show some equation later, but okay. And then for longitudinal model reproduced by the literal variance, because in this expression I can just replace this to plus minus 3% L. So this needs an additional input. So for L is slightly different, like somewhat different from the other conditions, but this is not a problem in our opinion because we can just do this replacement. So if you take the high energy limit, then you get is e to the fourth term. So E is the center mass energy, e to the fourth term, and that automatically cancels because now, so here G scalar is given by this. So we discover this from the bottom up. So we discover this kind of relation. And this automatically guarantees the cancellation with this is e to the fourth term, but E scalar term requires additional input from Higgs. So I think I can just explain a bit more about this point in this slide. So the last topic is about, so this is the last slide before finishing my talk. So high energy limit of the longitudinal modes are given by this expression. So you can just use this expression and replace this and then take the high energy limit and see what happens. And this is the expression. So here I think I'm taking the S and T to be like overall the same, so I'm just taking the fixed angle scattering. And then I get this expression. So this is e to the fourth term, and this is a scalar term. And then as you can see that because we get this G scalar is equal to this relation, so that kills this convolution, and also this convolution. So because of this relation, actually there is no e to the fourth term, but we still have this e scalar term. And I think that this fact by itself is well known in the context of the Feynman dynamic condition. Like e to the fourth term is kind of cancelled because of the gauge symmetry, gauge invariance. And a scale term needs an additional input, for instance, like the Higgs and so on. But we claim that it is like we found it for the first time in terms of Longchamp method, not the Feynman dynamics. And then this scale term needs an additional input. And for instance, here we can discuss Higgs again in Longchamp method with LT. So now what we have to do is that we also introduce a Higgs as a particle content from the beginning and do the computation. The 3-point amplitude is given by this, and 4-point amplitude you can also compute, and that is given by this. And from that you will get this kind of relation. So GWH scalar is going to be equal to this expression. So UV completes the theory, and then this relation of course holds in the standard model. But our main message is that we could derive the fact that this e scalar for e to the fourth term and e scalar term they are somewhat different. Like they're having a different relation. Like e to the fourth term is cancelled just by the gauge symmetry without any interaction and so on. But e scalar term is an additional input. So that's sort of our.
So you discovered the Higgs.
Yeah. I don't say that, but because I feel like I'm not. Yeah, you can say that. Okay, so this is the end of my talk. So I will summarize my talk. So first of all, on-chain method is an alternate way of computing scattering amplitude. So, and then especially we think that our LT shift is kind of good because then it works for the massive scattering amplitude with any combination of the LFTs. Not any because for longitudinal is not working by itself, but that is not an issue as I said. And also we first applied to the QD and that correctly reproduces amplitude and result in the previous confusion about the conduct term. And we also applied it to the electric theory and reproduces amplitude including gauge 4-point in conduct term. This is really coming from Z scale term, so that is kind of interesting for me. And then, so as I said, we are kind of now finishing to write a draft. Not finishing, maybe started writing a draft about the theory, and hopefully we can finish it soonish. And after that, we're kind of wondering which direction we want to go. Maybe one direction we can go is like a higher spin, or maybe we can also apply this kind of recursion relation to the recursive proof of the color duality or some like nice properties of the amplitudes, but in a massive theory, not a massive theory. We are also wondering whether we can say something about the loops. I'm not completely sure because the complex structure will be defined. But we'll look into it. And I'm also wondering is there any other interesting direction? So if you have any idea or something about possible directions, then I'm very happy to have a chat. So with that, I stop here. Thank you.
We did have a lot of questions during the talk, but if no questions.
So if I gave you a theory with a massive vector, like with some self interaction, no Higgs. So with the inputs you put in, you basically uniquely recover the Higgs. But I could also, I mean,
I don't say it is unique because it is more like our choice. So we uniquely discover the cancellation with this e to the fourth term. But how to cancel this e scalar term is not unique because here I just put Higgs by hand in a sense.
basically now that you have another.
It's known that from top down, it's known that you can also use like spin one another.
Yeah. Concept right.
But there's something effectively then acting like a spin.
No, not the Higgs, spin one.
Okay.
Spin one. Like a
Yeah.
maybe
Actually,
a
you
bunch
can-
of spin ones. Like,
Yeah, so it's how.
This is more like a technicolor issue.
Yeah, you can also
Okay.
see it. Actually, you can also see it from this expression because once you have an initial like z prime or something, you will get an initial convolution like -3 GWW z prime times z prime square or something. And by combination, like you can just say that this specific combination cancels this term. And the problem is that in that case you have to also consider like a z prime scattering. And there you need more like resonances, and in the end, it will become more like a tower.
Yeah, actually, that was the question. So then can you reconstruct the tower from that also? Can you categorize what the possibilities are? That could utilize the vector boson scattering here.
So in principle, what we can do is that yes, so in principle, what we can do to answer your question is that we can, so here, I would say like Higgs is starting from scalar, like resonance. So we can just start from zero, spin zero particle, spin zero particle, what happens, spin one particle, and then what happens. In principle, we can also add a spin two particle and see what happens and so on and so forth. So we can, in principle, do that.
Yeah.
And in that case, like what you have to do is that not only this process, but you also have to consider like this intermediate particle can also be as an external particle, right? So you also have to, like for instance, also Higgs case, you have to make sure that Higgs scattering is okay. Also, this spin one particle case, as I said, you have to make sure that this like if you put this particles as an external particle, and is it okay or not? And then in this also spin two particle, you can also do the same with spin three and so on and so forth. So in principle, you can do that. You can do that analysis. I think we are kind of thinking about how much we want to explore those kind of different possibilities of UV conditions. Probably we do not consider like a spin to particle because it's going to be kind of messy. Yeah, in principle.
Spin two, somehow adding spin two should be different from spin less than two.
Right.
Physics should change very dramatically.
There's a pseudo theorem saying that spin two cannot univariate that. But it doesn't have the right, but it's just some pseudo theorem.
Yeah.
Examples.
Yeah.
But
I guess Sam is saying that maybe if you add spin two, you need an tower or something.
Well, even spin one, I think in the known examples you have it's not like technicolor, right? You have a techni-row somehow unitrize a little bit, and then another A and that unitrize a little bit, and so on.
So
it's always there's something.
So what you're saying is like spin one case you need a spin one particle by infinite tower, and then spin two case like you have this rigid
high spin tower.
and that might be possible. I don't know.
Yeah, we probably need the high.
A string theory like
I mean, a KK extra dimension will also give you a tower.
Yeah, that's the spin one thing seems to be like a KK kind of.
I think Nathan's thinking of it as coming as composites from some.
It's the same series. It's the same series. Actual dimension and the composite is the same series. So there the unitarization, actual dimensional language, the reason that the unitarizes is because there is a higher dimensional gauge symmetry. Therefore, you unitarize.
Yeah. So,
but the representing your KK compactification, then this will give you so you need all the full tower in principle to recover full 5-dimensional gauge symmetry. So it's
So one other question, which is more connected to the kind of physics going to have very supersymmetric gauge theories. If I gave you just a photon, f mu nu squared, and then I gave you a higher derivative interaction like f mu nu to the fourth, coupled to some adjoint Higgs in this case. So it's just suppressed by some scale. F mu nu to the fourth suppressed by some scale. And there's some adjoint Higgs floating around here. Could you, it's not adjoint is the wrong word, it's neutral Higgs, it's just a neutral scalar in this case. Could you, from an amplitude approach, reconstruct this as a spontaneously, the Coulomb branch of some spontaneously broken gauge theory, like SU2 broken to U1 by an adjoint Higgs, give me a photon, a scalar, leading order interactions of the photon very far out, and the Coulomb branch are free, and then there's some irrelevant operator that corrects this. But the typical completions are like non-abelian gauge theory. But could one actually predict that you need to have W bosons, say, in that theory?
I'm not. So first of all, I don't know how to answer that question. I'm not completely sure. I'm a bit skeptical about you can reconstruct that. Like, do you have like the towers of the higher dimensional operators?
In principle, yeah.
Something, and then you have some specific constant between them.
Yeah.
Something if you assume that it is coming from some UV theory. Like, I'm thinking more about Euler-Hasenberg term, for instance, like, you integrate the electron, and then you get those kind of, towers of the operators, right?
Yeah.
And if you just integrate the electron, then you have specific like coefficient for them.
That's
and then by just checking those kind of numbers, you can, in principle, say that, it must be really coming from the electron because this and that operator satisfy those kind of coefficients. Here, I kind of feel like I'm a bit skeptical about you can reconstruct that information from this program because which one? Maybe I can just go back to the dimensional analysis. So here, or maybe, yeah. So here, actually, I have to input this higher dimension operator information as a boundary term. So as I said, like if the, you cannot say that that's behavior is bad. Like, if you cannot say that that's behavior is good, then you have to add this b infinity by hand. So kind of feel like Euler-Hasselbalch Lagrangian case, what you have to do is that you actually have to put this b infinity just by hand for each order. Like, you can consider like, 4 photon interaction, 6 photon interaction, and a photon interaction. And some of them should be reconstructive because some of them should be coming from like a kind of the product of the lower point amplitude.
Yeah.
But on top of that, you also have this corner interaction that is coming from the highest like a dimensional operator of this Euler-Hasselbalch Lagrangian or something. And that you have to actually put by hand. And maybe there I kind of feel more like, you're just choosing the coefficient by hand.
So there's no principle that you see that could, say if I add the f to the 4th, that I have to add, say, f to the 8th with some specific coefficient, the f to the 10th with some specific coefficient.
Yeah, so naively, that's what I do. I don't know whether you can input some additional like a symmetry or something to input
fix
some
the-
specific choice. But naively, I kind of feel like, at each order, you just choose some b infinity, and then that coefficient is your choice. So it's more like, you just put that information by hand, not something like you reconstruct. That's my feeling, but maybe I'm wrong.
Obviously, it's not unique, right? You can
Yeah.
you can UV complete f to the 4th, f to
Yeah,
the 8th,
and then that is corresponding
with different series. So obviously, it's not unique.
Yeah. So for instance, we can have the electron, but also the muons and so on and so forth. So
You can just add some other things. Yeah, anyway, yeah.
Yeah.
So it's
So
not-
my impression is towards like, you cannot reconcile the information, but I'm happy to.
But there are positivity bounds on the derivative terms for unitarity, like the leading ones anyway. And
Other than they are positive, it's very little.
yeah, just that they're positive here, but there isn't, I think, analogous bounds for the higher order ones. So, even if one could just say that they have to have a fixed
Oh,
height.
there are higher, there are ones for the higher.
No,
order.
I think
Oh,
you
yeah?
are saying f to the power 6 or something, right?
F the, yeah, maybe.
I think it's
there is
basically 8, 12,
Yeah, dimension
maybe
8.
16,
Yeah, so
Yeah.
so
What
the dimension 6, you don't.
you don't.
Dimension 8, you do. It's just have something to do with whether you
I
have.
think external, so in general, you have like an external correlation, internal correlation, and then depending on like how much you have, like, like how much exponent you have in a denominator, something like they,
It only
like,
depends on where you go into using the crossing relation.
yeah,
Whether
exactly.
that term
Like,
changes sign or not.
yeah, exactly.
If it
So
doesn't
dimension
change the
six-
sign, then.
So yeah, I think at dimension 6 case, you also have to care about the correlation from the infinity. Like a higher dimension, you can forget about the correlation from the infinity, but you still have to, like, you have different signs, correlation from the S channel, U channel.
I see.
And like, that's why multiple, like, dimension 8, 12, 16, 12, 20 or something, like, you can say that this is positive. But that is somewhat different from, like,
Okay, any more questions? If not, let's thank Yohei again.
Spin 3 up is